Greetings, Shaler. Welcome back to Chemistry Notes. This is the final note video for Unit 2 Chemistry. It is note video number 14. Alright, so we're going to wrap off the note packet. We've learned all about bonding. Now in this note video we are going to talk about the different kinds of chemical reactions, which you did a lab on with the Reaction Action Lab. We're going to talk about combustion specifically, and a couple of other things here to wrap up our chem knowledge. So what are the four kinds of chemical reactions? Well, one of them is called a synthesis reaction, and a synthesis reaction occurs when simple items combine to make more complex items. So one good example would be sodium combining with chlorine to make sodium chloride or salt. Another one would be, and this is a more balanced chemical equation here, well, I mean this one's balanced too, but this one actually has some coefficients. If we combine magnesium with nitrogen gas, we can get magnesium nitrate. And if you notice the balancing of it, in N2 and N2, Mg3, so we would need 3 of them. And you should be able to look at the periodic table and look at the valence electrons and figure out that it would take 3 magnesiums and 2 nitrogens to actually make a molecule. You did that with the Lewis dot homework assignment. Magnesium nitrate is a compound that's used in fertilizers. So whenever you're spreading fertilizers in your garden or your lawn, it probably contains magnesium nitrate. So synthesis reactions are when you are joining simpler things to make them into more complex things. Synthesis means to build. In the Reaction Action Lab, the synthesis reaction was the one where you burn the magnesium and when you rusted the iron. They're exothermic. A decomposition reaction is the opposite of synthesis. It's when you take complex molecules and you break them down into simpler ones. I mean, we use the word decomposition for when things rot, and that's essentially what's happening. You have a complex material that is turning back into simpler materials and nutrients that go back into the soil. So a good example of this would be chalk, which, hey, you made in the lab. But if you heat chalk up, it turns into these two things. So we have one molecule turning into 2 molecules. That's why it's a decomposition. CaO is something that we call quicklime, and it's a really important ingredient in cement. If it wasn't for quicklime, cement wouldn't harden the way that it does. And it gives off carbon dioxide. And remember, if something is needed for a chemical reaction to take place, we write it over top of the arrow. So chalk with heat yields quicklime and carbon dioxide gas. Another one is one of the reactions that we did in a demo, and it's the decomposition of peroxide. So here is hydrogen peroxide, H2O2, and in the presence of light, it yields water and oxygen gas. So for every 2 molecules of peroxide, we would get 2 molecules of water and 1 molecule of oxygen gas. And since light causes this to happen, that's why we keep peroxide in opaque brown bottles, to prevent that from happening in your medicine cabinet. So it's decomposition if we have 1 molecule turning into more than 1 molecule. The other 2 kinds of reactions are both replacement reactions. There's a single and a double. So a single replacement reaction occurs when 1 atom changes place with another atom. So this is another reaction that we did in lab. This is the one that we used to make hydrogen gas. We had zinc and we combined it with hydrochloric acid. So what happens is the zinc and the hydrogen switch places, and we end up with zinc chloride and hydrogen gas. And notice this one didn't take anything over the arrow, because it will happen just because the 2 things are together. It doesn't need anything to make it happen like heat or light. It's spontaneous, we call it. Double replacement reactions are the same as single, except instead of 1 atom switching places, we have 2 atoms changing places. So here we could have copper oxide, or cupric oxide, mixing with hydrochloric acid to make copper chloride and water. This is one of the chemical reactions that causes statues that are made of copper to turn green. This is a green kind of color, and notice if we have copper and it's reacting with an acid, we can make this. And this is why acid rain causes those nice kind of like copper bronze statues to turn green over time. It's essentially why the Statue of Liberty has that kind of green color to her. So just to note, remember, single replacement reactions, you have one switcheroo going on, and in a double replacement reaction, you have two switcheroos going on. This graph shows the starting energy of the reagents, and remember, reagents are what come before the arrow in a chemical reaction, compared to the energy of the products, so how much free energy you have after a reaction. And this little hump here represents the change in energy while the reaction is going on. So if we look at the graph, the x-axis is has to do with like the time of the reaction. The y-axis is E, which stands for energy, and as you go up, energy gets bigger. As you go across the x-axis, the time gets longer. So here we have our starting ingredients, the reagents. Here we have the finishing products. And if you notice, the products have a lower amount of energy than the reagents. You can kind of think of this as like potential energy. It's like the chemical energy that's in the bonds of the molecule. Well, if we had more energy when we started than we had when we finished, remember that energy, you can't create it or destroy it. So it's not destroyed. It has gone somewhere else. So this means that this chemical reaction has caused this amount of energy to be given off. And we can think of it as being like given off into the air, typically as heat. It's an E. But it could also be given off as light or anything else. But typically it would be heat in this kind of a situation. And that's why this would be an exothermic reaction. Because our final products have less energy than what we started with. So that means this energy had to go off into the environment. And we would feel that as heat. On the flip side, I guess we'll get there later. This little hump up here, notice we have to put energy in before we get energy out. So the amount of energy that we see above the starting line is the amount of energy that we're putting in, and the difference between the starting line and where we finish is how much we're getting out. This is called the activation energy, and this is the energy that it takes to start a chemical reaction. So anytime that you see on those arrows like heat, well, it would take this amount of heat right here to start the reaction. If it's light, it would take like whatever amount of energy in light that it would take to start the reaction. So anytime you have this hump up, then you need energy to put in before the chemical reaction can take place. If you don't have a hump, then it's a spontaneous reaction, as we saw with the zinc and the hydrochloric acid. It wouldn't have a hump at all because it would just happen. Well, we can affect how fast, or we can alter and change how fast a chemical reaction takes place by changing several different variables. One, we can change the surface area, because remember, in order for a chemical reaction to take place, two molecules actually have to run into each other. They have to make contact. Well, if we increase the surface area of the things that we are reacting together, we increase the likelihood that they will actually run into each other. For example, and I'll do a demo on this, but for example, let's say we had a giant block, we'll write down here, let's say we had a giant block of sugar, giant cube of sugar, and I was pouring some kind of a chemical on it. We'll say it's some kind of like a green. We're going to pour it on there and it's going to cover the block. Well, it can only react with the surface of the block of sugar. So the only reaction that will take place is where they're actually touching. But let's imagine that we are going to like take a big hammer and we're going to smash, it's not exactly the pen I needed, and we're going to smash this block of sugar, and we're going to turn it into a bunch of smaller cubes. Now we're going to pour the green stuff back over it, and notice we're covering more surface area with the green liquid, so we can have more contact between the compounds, and you can have reactions happen at a faster rate. Whereas this one over here would have to like eat into the block in order to continue to react. This one has more contact with the sugar, you're going to get a faster reaction. Temperature is another thing that you can change to cause a reaction to happen faster, because if you increase the temperature, you increase the speed of the molecules, and if they're moving faster, there's more of a chance of them to run into each other. If you cool it down, you slow it down, and you reduce the reaction. This is why if you take your glow sticks around Halloween and put them in the freezer, they'll still be glowing the next day, because you slow down that chemical reaction that's causing the light to give off. This is why putting food in the refrigerator makes it last longer before it rots, because that rotting is a chemical reaction that takes place. Concentration is another way that we can affect the speed. Concentration means like how many solute parts there are in the solvent. The more closely that you get that solution to saturated, the more concentrated that it is. So the more concentrated that your reagents are starting with, the more closely packed together those molecules are. So the less distance that they have to travel before they run into each other, and the faster the chemical reaction will take place. In the reaction action lab, I asked a question of how would adding more water to your double replacement where you made the chalk, how would adding more water affect the chemical reaction? And remember, water wasn't one of the things that actually reacted, but adding more water would cause the concentration to become more dilute, and you would still make the same amount of chalk, but it would have taken longer to make the chalk. The last two are things called catalysts and inhibitors. And they work the same way, but with opposite effects. So remember, these molecules have to run into each other to react. Well, what you're going to learn more of in college chemistry is that they have to run into each other, not just touch, but they actually have to run into each other with just the right angle of attack in order to have a chemical reaction. Well, one of the things that catalysts can do is catalysts can help those molecules actually hit at the right angle. And this is what a lot of enzymes do in our body. Enzymes in our body are special proteins that cause chemical reactions that we need for life to happen at temperatures that are much lower than they would normally happen on their own, the 98.6 degrees. Well, these enzymes in your body actually kind of grab a hold of the molecules and they force them to come together at just the right angle. That's how the enzymes work. But there's lots of different catalysts, things that aren't necessarily in bodies and aren't necessarily proteins and whatnot. And they lower the activation energy. What they do is it requires a smaller hump before those two molecules will react together. Inhibitors do the opposite. Inhibitors prevent the molecules from hitting each other in just the right way to react, which means it would take more activation energy to cause them to collide in the right way. So if we look at this reaction down here, all right, so if our activation energy is this hump, if the green one was normal and the red one is what we get, all right, let's just go with what it actually says. I wasn't reading the words. If the red one was normal, it would require this much energy to react. But when we add the catalyst, it causes the hump to lower, which means it takes a smaller amount of energy to trigger the reaction, but you still have the same exact chemical reaction. You still finish with the same things down here. Now, remember, the most important thing to keep in mind about catalysts and inhibitors is that they are not one of the reagents or one of the products. They don't actually take part in the chemical reaction. The molecule of the catalyst or the molecule of the inhibitor is exactly the same in the beginning and in the end. It doesn't change. There's no chemical reaction that occurs with this actual catalyst or inhibitor. They just assist in helping the other things actually react. which is why you won't see catalysts or inhibitors written in either side of the arrow in a chemical equation, but you will see them written over the arrow, sort of like you need heat or you need light. Sometimes you'll see another chemical compound written over the arrow. That means it's either a catalyst or an inhibitor. Mostly, if it's written over the arrow, it's probably going to be a catalyst. All right, the last thing we're going to talk about is combustion. Combustion, by definition, is any exothermic reaction that occurs between oxygen gas and a fuel. It could be any fuel. And people who study fire, like firefighters and other people who study fires, forensics people, they refer to this reaction using the fire triangle. So to have fire, you need oxygen, you need fuel, and you need heat. So if you want to stop a fire, if you want to stop a combustion reaction, you have to break the triangle. So you have to remove one of the sides of the triangle, and then you can no longer have fire. So a lot of the ways that we do this, one of the most immediate things that you can do if you see a fire is to smother it. And that's when you cover the fire up to prevent air in the room from getting to the fire. If you prevent air from getting to the fire, you are breaking the oxygen side of the triangle. And if you remove all the oxygen, the fire will go out. Now, don't do this with your hand or with something that is flammable itself, because when you cover it, there's still some oxygen in there, and if whatever you cover it with is flammable itself, that can then catch on fire. So in a kitchen, the best thing to do if you get a fire in a kitchen and it's like a fire on your stove and it's a pot, have a lid handy and cover that pot, and the fire will go out. The most common way that we put fires out, though, is to spray water on them or dump water on them. Now, never do this in a kitchen fire. If you have a kitchen fire, most likely it is a grease fire, and if you dump water on it, you make things a million times worse, and that's how people burn their houses down. So if you have a kitchen fire, and it's because you're cooking with oil, you always smother it. Never, ever, 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 ever dump water on it. It's crazy. If you want to see what happens, there's several YouTube videos that show what happens, and it's wild. Actually, I think the aura, I don't know if the aura in the notes is about that or not. Anyway, so spraying water on a fire causes the fire to go out, probably not for reasons that you think. It's not because the water won't burn, but it's because when you spray water on the fire, you coat the burning material with the water, and that actually forms a barrier that separates whatever's burning, like the wood, from the air, and that blocks the oxygen. And if you cut the oxygen side, you can no longer have fire. And the added benefit, the reason water works so well, is because it has a really high specific heat, which sucks up a lot of the temperature without actually raising the temperature of the water, and that actually breaks this side too. So spraying water on a fire is the best thing to do, just not on a grease fire. Fire extinguishers work. Most fire extinguishers, there's 3 different kinds of fire extinguishers, and you use different kinds for different types of fire. But the most common kind that you'll come across has dry ice in it. It has solid CO2, solid carbon dioxide. And when you spray it, that solid quickly sublimes, so it goes from a solid to a gas. And CO2 is more dense than oxygen gas. And if you remember from the demo, oxygen gas wants to fall because oxygen gas is more dense than air itself. Well, carbon dioxide is even more dense than oxygen gas. So when you spray a fire extinguisher on a fire, you actually end up creating an invisible blanket of carbon dioxide gas over top of whatever is burning. That separates whatever is burning from the oxygen gas in the air, and it causes the fire to go out. This is also, though, if you keep in mind this CO2 kind of thing that's going on, this stuff is more dense than oxygen gas, and some of the things that are created when wood burns, one of the things that is created is carbon dioxide that's given off. So in a house fire, they used to tell you to like crawl and go across the floor because the smoke rises, but the problem is that the carbon dioxide can fall down, and there's no oxygen in that bottom level. So you never want to try to crawl out of a burning house to get out of the smoke. You want to just kind of duck your head, stay in that middle zone, and get out as fast as you can before you run out of oxygen. It's typically not the fire in a burning house that causes the person to become incapacitated. and then eventually die, it's usually because they run out of oxygen. They can't breathe. They don't get out of the house fast enough. They run out of oxygen and then pass out. And then the fire overwhelms them. Baking soda, hey, something we're going to be doing soon in lab. When you decompose baking soda with heat, thermal decomposition, one of the things that's given off is carbon dioxide gas. And it works the same way. It pushes the oxygen away, and then you get the fire triangle broken. So dumping a lot of baking soda on a fire will also cause the fire to go out. So as long as the fire triangle is intact, you will continue to have combustion. There is a coal mine in the middle of Pennsylvania called Centralia. And in 1962, they accidentally caught all the coal in the mine on fire. They were actually trying to do a controlled burn on purpose in a garbage dump, and the fire spread into a coal shaft and caught the mine on fire underneath the town. And it has been burning ever since 1962. They have not been able to put it out because they've not been able to break the fire triangle. This has resulted in like the town needing to be evacuated. It's like a ghost town. And it's actually what the movie and video game Silent Hill, it's the town that was based on. All right, that leads us to our last booby trap in the chemistry unit. And class is coming in, so I need to wrap it up. Everybody have a nice day.